Hello, everyone, and welcome to this first session of Exploring Multiple Universes. I'm James B. Barbieri. I'm the Associate Program Director here at the Carr Center, and I'll be your host for today. And as a host, I'm here to help you throughout the call, so any problems, feel free to drop a message in the chat, either to me or to Eleanor. Before we begin, I'd just like to remind everyone of a couple of Zoom rules for this session. First of all, we ask participants to turn off your microphone during the presentation and discussion, just to ensure a good quality audio. But at the same time, we do encourage you all to keep your cameras on, as seeing everyone's faces and reactions creates a nice, inclusive education environment. But you're very free to just keep your camera off if it makes you feel more comfortable. During Q&A and discussion, if you'd like to make a contribution or ask a question, you can use the raise your hand function on Zoom, which is at the bottom of your screen under reactions, or physically raise your hand. If I spot you, I'll call out your name and you can ask a question. Or if it makes you feel more comfortable, you can ask your question in the chat and I can read it out for you. And finally, this session is recorded for archival purposes and for you all. The session will be available to you all about 3 days after this session. You should all receive the link to it. If not, just let us know and we can help you out. Okay, so now we can start. Today we have the honor of introducing Professor Bernard Carr. Bernard is the Emeritus Professor at the Queen Mary University in London. He's a Fellow of Trinity College, Cambridge. Bernard was supervised for his PhD under Stephen Hawking, and his research area is mainly in cosmology and astrophysics, and covers topics such as the early universe, dark matter, black holes, and the anthropic principle. Today, Bernard will talk about the multiverse and the limits of science. And with that, I'll pass it over to you, Bernard. A very warm welcome.
Thank you, James. So I will share my screen. So I hope everybody can see my opening slide. Well, first of all, I should say it's a delight to be talking to you. Of course, I'm rather sad that I'm not actually talking at the Parry Center itself. Maybe in some parallel universe I am talking in the Parry Center. But on the other hand, maybe an advantage of this is that I know that there are people from all over the world who are listening in, and maybe they wouldn't have been listening in if we had physically been in Parry. So anyway, I'm delighted to give the opening talk in this series. My title is The Multiverse and the Limits of Science. And my professional field is cosmology, so I will be talking in my cosmological capacity in this talk. I will give another talk later on where I'll be sort of talking about more philosophical issues. And I have less expertise in that area, but in the context of cosmology, I suppose I have some expertise, but of course that doesn't mean I'm right. So, and you'll notice that my second title is And the Limits of Science, because one of the issues I'm going to discuss is the multiverse a scientific concept? And that will link in with some of the other talks. Now, in 2007, I think, I edited a book called The Universe or Multiverse. And that was really one of the first books that appeared on the subject. And I was quite proud of the book because it contained a variety of experts from many different fields, from cosmology, from particle physics, from philosophy, even from theology, and also people with very different views about the multiverse. I mean, as you'll come to understand if you don't already, the multiverse is a rather controversial topic, and by no means all cosmologists believe this, but that some eminent ones do. And that's why there was a question mark in the title. And although I have to say my personal view is a rather positive one. And I'll just start off by making, a brief statement, which I will read out. Recent developments in cosmology and particle physics suggest that our universe, rather than being unique, could just be one of many universes. Since the physical constants can be different in the universes, the fine-tunings which appear necessary for the emergence of life may be explained. So here you see that there's two concepts here. There's the concept of the multiverse, but there's also the concept of fine-tuning of the constants, which are sometimes called the anthropic tunings. And in my mind at least, these two concepts are very much linked, so I'm going to talk about both of them. But I have to say they're both contentious. A lot of physicists don't like the anthropic principle at all. They have almost a violent antipathy towards it. The multiverse is also controversial, though perhaps not quite so controversial. But the key point about the multiverse is it is the most natural physical explanation of these anthropic tunings. And I thought I might just start off explaining where this book came from. We had three meetings, which are all actually funded by the Templeton Foundation. And the first meeting was in 2001 in Cambridge. That was called Anthropic Arguments in Fundamental Physics and Cosmology. And there's a nice little picture there. Obviously, that's, well, my goodness, 20 years ago now. And I won't introduce all the people, but some of you will recognize there is Stephen Hawking, George Ellis, Martin Rees, John Barrow, Lee Smolin, Andre Vallende, Jim Hartle. The physicists will know all these names, Max Tegmark. Oh, and there's me. I had a beard in those days, so I've changed a bit, but it was 20 years ago. So, and that was really one of the first meetings really on the topic, at least among, physicists and cosmologists. And so I think it was quite an important meeting, but there were two other meetings. There was a meeting in Stanford called Universe or Multiverse, after which the book was titled. And then there was another meeting in 2005 in Cambridge called Expectations of a Final Theory. And I just want to quote from that because the attitude to fine-tuning has changed over the years. I mean, when I first started working on the topic, it was very unpopular. It was regarded as philosophy or even theology. But the attitude changed. And there's a quote from Frank Wilczek, actually, in the book. He was talking at the third meeting, and he said the previous gathering had a defensive air. It promoted... to be honest, I can't read the edge of my slide because that's fine. It prominently featured a number of physicists who subsisted on the fringes, voices in the wilderness, who had for many years promoted strange arguments about conspiracies among fundamental constants and alternative universes. Their concerns and approaches seemed totally alien to the consensus vanguard of theoretical physics, which was busy successfully constructing a unique and mathematically perfect universe. Now, which means 2005, the vanguard has marched off to join the prophets in the wilderness. And so it's true that in just the 4 years between the first and the third meeting, there'd been quite a change, primarily because so many, eminent physicists, including some of the ones you saw in that picture, were taking the idea seriously. So I would say that the attitude of the skeptics was it makes no sense and I hate it, had rather become I hate it. You'll find there's still people who hate the idea, but nevertheless, I think people are accepting that it's got more rationality behind it than was originally thought. Now, as regards this talk, I'm going to get across 5 messages, so I'll say what they are in advance. The first message is what we call the universe is always growing. And in this part of the talk, I'm really going to be giving you a historical overview of the history of cosmology, because I understand you're not all cosmologists, so I'll keep this at a fairly popular level. But I think it's important to see how the subject of cosmology, through its evolution, has actually led to a change in the concept of what we mean by universe. Then I'm going to talk about the message 2. I'm going to argue that the observable universe is a minuscule part of a larger physical reality. And that is almost uncontestable. Within the context of the Big Bang theory, you can only, where the universe began 14 billion years ago, light can only travel 14 billion light years. And so it's inevitable the universe extends beyond that. Message 3 is going to be something is going to be the main theme, that both cosmology and particle physics suggest that there could be many other universes. Now, we talk about the multiverse as though there's only one multiverse, but actually the concept of a multiverse arises in many different contexts, some coming from cosmology and some coming from particle physics. And so when people say, well, do they believe in the multiverse? You really have to make it clear which multiverse you're talking about. And then message 4, which I've already mentioned briefly, I'm then going to argue that the multiverse naturally explains the fine-tunings, what are sometimes called the anthropic fine-tunings. And indeed, you might say that's the fine-tunings are perhaps the at least indirect evidence for the multiverse. And then the fifth message is that the nature of legitimate science changes, because you remember the subtitle of my talk is The Limits of Science. And the point I want to get across is that as our understanding of the universe changes, so does our concept of science and what we call legitimate science. So when people argue, well, is the multiverse a scientific concept? It's going to hinge crucially on what you mean by science. So with that, I'm going to start describing the history of astronomy, essentially. And as I'm sure you know, humanity started off with the geocentric view, in which the Earth is at the center and the planets move around, but the stars in the heavens are fixed. Nothing can ever change. So that's an idea that goes back to Plato in 400 BC, roughly. And so here is a sort of a slightly more precise picture with the Earth in the middle. We've got the planets going around us, and then we've got the fixed stars. And so the crucial thing in the Greek perspective is that the stars, the heavens, cannot change, because that is the domain of the divine. Now, the first revolution came when the astronomer Tycho Brahe, he was taking a walk one evening in 1572, and he observed a bright line in the sky. And that was actually a supernova, an exploding star in the constellation of Cassiopeia. And what was strange about this was that he noticed that during the course of the year, it didn't move. Now, of course, if its object is at a distance, as the Earth goes around the sun, the apparent angle of that will change. And the funny thing was that the angle of this bright star didn't change. And so he knew from that it had to be at a great distance. And in fact, he knew it had to be way beyond the planets. But that was impossible, because according to the cherished view of the Greek of Aristotle, the heavens couldn't change. And so people said it can't possibly be true. It can't be at that distance. And he got very annoyed about that, because people were not believing his observations. So he said it in Latin, but I'll just translate it into English. "O thick wits, O blind watchers of the sky." This is what he said in the preface of his book, De Nova Stella. And the point was, he was annoyed because people were taking as sacrosanct the traditional ancient belief, even though it contradicted what the evidence of their own eyes. And really, that has an important lesson, and I'm going to give you a few lessons during this sort of historical overview. And the first lesson is the theoretical prejudice should not blind one to the evidence. And actually, later on, you'll see that the evidence here, I'm referring to the fine-tunings. Not everyone may believe the evidence, but at least that would be the claim. And so that was really important, because it demolished this cherished view that the heavens didn't change. But then, of course, and that was 1572, but actually a little bit before that already, the heliocentric view had overcome the geocentric view, of course, through the work of Copernicus. And because of Copernicus, one realized that the planets, the Earth goes around the sun and not the other way around. Here is my favorite picture of Copernicus in a conversation with God. Well, of course, after Copernicus, I mean, for example, Galileo realized that our sun was actually not so special. I mean, he realized that our sun was just millions of billions of stars which made up the galaxy. And so it was the idea that something existed beyond the solar system, and which would vary, was pretty soon established. But nevertheless, for a long time, it was assumed that what's beyond the solar system could not be part of science. And here's a famous quote from Auguste Comte, who was a philosopher, and he said, "Never by any means will we be able to study their chemical composition." He was referring to the stars. "The field of positive philosophy lies entirely within the solar system, the study of the universe being inaccessible in any possible science." So he wasn't saying things don't exist beyond the solar system. He wasn't saying stars couldn't vary as been observed by Tycho Brahe, but he's simply saying it's not science. And that's one of the questions I'm going to be always asking: is it science? And unfortunately, he soon turned out to be wrong, because a few decades later they discovered spectroscopy. And of course, spectroscopy meant that by looking at a star, you could analyze the spectrum of light and you could get physical information about the composition of the star, and thereby it became part of science. So that also has an important lesson. The second lesson: new observational developments are hard to anticipate. So when Comte said it couldn't be part of science, he'd failed to anticipate a new observational development, namely spectroscopy. And the history of astronomy has similar episodes. Well, then, of course, we had now got the galactocentric view, because it was realized that Galileo, as I said, Galileo himself had realized that the sun is just one of billions of stars, and those make up the galaxy. And so at this point, the idea was that the universe essentially is the galaxy. Now, or what was then called the Milky Way. I mean, I'm sure you know the Milky Way is the band of light you see in the sky, at least if you're away from the city lights. And when you look at that band of light, you're looking at a disk of stars, which makes up the Milky Way galaxy. And even at the turn of the 20th century, it was assumed that the galaxy was the universe. And actually, in the early models, like the Captain universe, our solar system was right at the center of the galaxy. So there was still a tendency to try and make us as central as possible. But of course, we now know the modern view is that here is the galaxy. It's got a disk, it's got a bulge in the middle and a halo around it. And we know the solar system, it's about 8 kiloparsecs from the center. So it's not in the center at all. But anyway, so that's the modern view of the galaxy. But the point was, the assumption was still that the galaxy was all there was. And people had speculated that there were things outside the galaxy. Even the philosopher Kant, for example, had speculated there could be other galaxies. But by and large, this is a minority view. And for example, Ernest Rutherford, the famous nuclear physicist, I think he was head of the Cavendish, he said in 1908, "Don't let me hear anyone use the word universe in my department," because basically he just thought it was philosophy. And this was 1908. Now, then in 1921, there was a famous debate as to whether there were actually any objects outside the galaxy. Now, on the one hand, we had Harlow Shapley, who believed that all the nebulae, which are the sort of lights that you can see in the sky, I mean, sometimes spiral structures you see in the sky, he thought they were inside the galaxy, like solar systems. On the other hand, Heber Curtis, another astronomer, he took the view that these objects were outside the galaxy, what they were calling island universes. And they had this famous debate in 1921, and actually it was somewhat inconclusive. But then, in the within I think 8 years later, the debate was resolved by the famous astronomer Hubble. And what Hubble did was he looked at the M31, the Andromeda galaxy, our nearest big neighbour, and he was able to measure its distance by looking at what are called Cepheid variables. These are stars which vary in luminosity, and their period of luminosity relates to their brightness. And he could establish that this galaxy, the neighbouring galaxy, was actually outside our own galaxy. He thought it was 500 kiloparsecs. It's more than that, actually, but at least he knew it had to be outside the galaxy, because that was bigger than the galaxy, our own galaxy size, which was well known. And so that was an enormously important development, because at that point we knew that the universe extended beyond our own galaxy. And Hubble then went on to make some other important discoveries. And the first thing he discovered was that the galaxies seem to be moving away from us with a speed which is proportional to their distance. And that's called Hubble's law. And it's going to be the basis of all modern cosmology. So the distance is actually is measured by the luminosity, and the actual speed is measured by the redshift. Because the galaxy is moving away, the light is redshifted. And so this was the famous picture which he first drew. This is plotting velocity of the galaxy against its distance. And this is the data. And he basically says, well, we can put a straight line through that. But notice it's not going very far. He's only going out to something like 2 million parsecs. A parsec is 3 light years. A light year is the distance light travels in a year. But that's not very far. It's only encompassing a few of the local galaxies. So you might notice that, there's quite a lot of scatter in that diagram. So you might have thought it was a bit of a guess to say it was a straight line. But it turned out that he was right. And then if you go to a later version of the Hubble plot, it goes out to much greater distances. It goes out to several billion light years. But now you really see that it really is a nice straight line. And indeed, Hubble's original diagram was only a few million light years. It was just that tiny little square in the corner there. So he was quite lucky that the data he had in that little square turned out to be consistent with the later confirmation of his law. Now, this law is called Hubble's law. So the velocity is proportional to the distance, and the constant which relates them is called the Hubble constant. And that has the dimensions of the inverse of a time. And if you take the inverse of the Hubble constant, you get a time scale which is, well, 13.7 billion years. Actually, it's 13.8 now, but that was correct at the time I first drew this slide. By the way, I'm not going to use many equations in this talk because I understand most people here are not physicists, but I'll use a few. And the interesting thing is, if you look at the older stars, which are the stars in the globular clusters, they also have an age which is just a little bit less than that, about 13 billion years. So that was that's nice confirmation that it makes sense. But the point is, of course, that if all the galaxies are moving away from us, how do you explain that? Well, it turned out that this expansion was actually predicted by Einstein, because Einstein in 1915 had his general theory of relativity. And this says that space itself is dynamic. Now, so the picture we always use, imagine a balloon with dots on it which correspond to the galaxies, and then you inflate the balloon. Now, in this balloon, this two-dimensional surface is supposed to be the 3 dimensions of space, because you can't really envisage 3 dimensions closed like that, but so it's just an analog. But you imagine that the balloon is expanding, and as you expand, as the balloon expands, as you inflate it, all the galaxies move away from each other, and that implies Hubble's law. And so Einstein predicted this, and furthermore, the Russian physicist Alexander Friedman, he realized this was a prediction of Einstein's theory of general relativity. In 1922, he wrote a famous paper where he showed that actually, if you can, although the universe is expanding now, this is the distance between galaxies as a function of time. there are different models. If the model is closed, so-called, the spatial sections are closed, it will recollapse. But if it's open, the universe will expand forever. And those are the basic so-called Friedman models of cosmology. Einstein, however, even though he thought of the theory, he did not know that the universe was expanding. Remember that Hubble was in 1929, Einstein's theory was 1915. So Friedman was actually predicting this as an expansion, but Einstein didn't believe that. He thought the universe was the galaxy and was not expanding, as we'll see later. Now, you might be slightly puzzled by the references to open, closed, and flat. So this is just the spatial sections. You're in the surface of the balloon. The spatial sections can either be closed. The universe can either go on forever, in which case it's open or flat, or it can be closed, in which case if you walk in a straight line, you come back to your starting point. But that's a technicality which we don't need to go into. But it's also worth pointing out that there was another person, a Belgian cosmologist and a priest actually, called Georges Lemaitre. And Lemaitre also had this model in 1927, but so he had his model independent of Friedman, but after it. And in fact, Lemaitre also predicted essentially Hubble's law and even made the first estimate of the Hubble constant. This was before Hubble, notice. However, his paper wasn't translated into English until 1931. And what's more, it only in a footnote did you have this reference to the sort of Hubble law. So he sort of didn't get the credit originally. The credit went to Hubble, but now actually he's remembered as the person also who invented, well, he was the person who realized, like Friedman, that the universe must expand, and according to this Hubble law. But the most important thing about Lemaitre is that he realized that if the universe is expanding, when you go back in time, all the galaxies are going to get closer and closer to each other. And therefore the universe must start in a very compressed state. So here's the famous diagram that you've got the galaxies now, but as you go back in time, they get closer and closer, and eventually you get, in theory, you get to a singularity where infinite density, but we don't know what happens at the singularity, but certainly we know there would be a Big Bang. And as I say, a Big Bang meaning a highly compressed state. And as I said, that highly compressed state would have been about 14 billion years ago. And it was Lemaitre who first realized this. But how did his contemporary react? Well, here's Einstein. Your mass is correct, but your physics is abominable. Remember, Einstein didn't think the universe was expanding. And here was Eddington, the other great cosmologist of the time. Philosophically, the notion of a beginning of the present. Oh dear, I can't see the end of the slide again. The order of nature is repugnant to me. And the reason it was repugnant to him was because probably he was very religious, and he thought that, you know, the creation of the universe had to be in the domain of God, and somehow the Big Bang seemed as though physics was impinging upon God. Maybe that was the reason, but in any case, these were the two great physicists of the time, and they rejected his notion. So you can get an important lesson from this as well. Don't be deterred by the opposition of great scientists. They often turn out to be wrong, and that may be true today as well. Of course, it soon became clear that, you know, the Big Bang model was, well, a few decades later, it became clear that it was correct. Another important development in the confirmation of the Big Bang theory was cosmological nucleosynthesis, because if the universe was in a compressed state, then a few minutes after the Big Bang, you would have had all the hydrogen burning into helium and other light elements. And I won't go into the details, but this was first realized in a paper by Alpha and Herman in 1946. And but the trouble is, again, most people didn't believe this because they thought, well, who can believe what the universe was like just a few minutes after it started? And so they said here, cosmology was then a skeptically regarded discipline, not worked in by sensible scientists. So most of their contemporaries were very skeptical about this. This was 46, notice the date. So another lesson, be prepared to apply known physics in new domains, because all they were doing was they were applying the known nuclear physics and combining it to the sort of cosmological model to show that you would get Big Bang nucleosynthesis. And that was the important thing, and they were absolutely right to do it, even though they got skeptical response. But then the real clinching evidence came in 1965, when Penzias and Wilson discovered the microwave background. And the microwave background, it's this radiation with temperature of about 3 degrees, which we see all around us. It's very, very smooth. The temperature is nearly the same everywhere. And that is meant to be the residual radiation from the hot Big Bang. And they got the Nobel Prize for discovering that. Nowadays, we can measure it much more precisely with satellites. For example, this is a so-called WMAP satellite. And the color represents the temperature. But so the color variations means that the temperature is changing. But the color temperature variations are very small. They're only about 1 in a million, or 1 in 100,000. So the temperature is roughly 2.7 degrees, but these are 1 in 100,000 fluctuations. Now, the more recent satellite is called the Planck satellite, and that's a European satellite, and it's the same basic idea. You've got these fluctuations, but it has much better angular resolution, and you'll see why that's important later. So, but basically the message is the same. And the reason you got fluctuations is because the fluctuations correspond to the little density fluctuations, which eventually give rise to galaxies and ultimately us. Now, anyway, at this point, and remember well, almost the present point, we might say we've got the cosmocentric view. And so in the cosmocentric view, we can imagine we're not at the center of the universe. Anyone can say this, but if we imagine we're at the universe, you remember that when we look to greater distances, we're looking back in time. And so you can look at, as you look to greater distances, for example, you will see galaxies and more distant galaxies. Eventually, when you look back to very early times, about 1 million years after the Big Bang, which is well before galaxies form at about 1 billion years, then you see this cosmic, you see what's called the horizon. In other words, well, you're seeing the microwave background, which is the microwave background which last scattered off the matter about 1 million years after the Big Bang. And that's essentially as far as we can see back. It's not quite the big horizon, the maximum distance we can see, but it's pretty close to it. And so this is what you might call the cosmocentric view, which essentially most cosmologists today would simply accept. I mean, it's an implication of the Big Bang picture. It's not saying the Earth actually is at the center of the universe. It might look as though we've returned to the geocentric view, because any other observer could say the same thing. It's just that where we can look at the universe from our particular position and see what it looks like. Now, so now I can give you my first message. And the first message is what we call the universe is always growing. So we've gone from the geocentric view to the heliocentric view, to the galactocentric view, to the cosmocentric view. And in some sense, not only is our concept of the universe changing at each stage, because at each stage people thought the universe was the Earth, the solar system, the galaxy, etc. But also in some sense you can see that already that in some sense the nature of science is changing because we're able to use observations to peer to greater and greater distances, and so science is expanding in some sense as well as the universe. But then of course the question is, what happens beyond the observable horizon? Because I've misspelled observable, it should be observable, not observatable. Because the point is that if the universe began with a Big Bang 13 billion years ago, then light can only have travelled 13 billion light years. Actually, it turns out it's travelled 40 billion light years because the space is expanding. But the point is you can't see further than that distance. But the universe itself doesn't end there. It's just that you can't see beyond that distance. It's just like if you're on a ship and looking at the ocean, you can't see beyond the horizon of the ocean. And this is where the story becomes really fascinating. Because let's go back to Einstein. And you remember Einstein thought the universe was static. And he introduced something in his equations in 1917 called the cosmological constant. And the cosmological constant was a repulsive term in his equations, which could balance gravity. And he invoked it because he wanted to have a static model, because he thought the galaxy was the universe. But then 1929, Hubble discovers the expansion of the universe, and Einstein realizes with horror that he missed a chance to predict the expansion of the universe. So Einstein in 1934 says he calls it the cosmological constant, his biggest blunder. But then, and so after that, most astronomers assumed the cosmological constant was zero because there was no need to invoke it. But then the remarkable thing was that in 1998, astronomers found evidence for it. And the evidence came because they were basically, you can plot the Hubble diagram, which I showed you before, but now you're using supernova, which are very bright, and you can use the properties of supernova to work out their distance. And you can plot a Hubble diagram. This is the redshift, the velocity again, against the distance, which is measured by the luminosity. And this diagram's a little bit technical, but all the different cosmological models are represented by lines here. The data is represented by these black points. And the point is, you can see the model that works best is what's called the Einstein de Sitter model. So it's the model which has a cosmological constant. Sometimes called the lambda CDM model, because lambda is the symbol used for the cosmological constant. So the normal model without a cosmological constant doesn't work. And indeed, the people who discovered this got the Nobel Prize. But until then, almost everybody had assumed that the cosmological constant was zero, because this was Einstein's big mistake. And so lesson 5, majority opinion and expectation is often wrong. And so when Einstein said lambda was his biggest blunder, I mean, arguably his biggest blunder was saying it was his biggest blunder, because it turned out it was right. Now, what is this cosmological constant? In some sense, it's the vacuum energy. It's sometimes called dark energy. And it's got a density, and indeed it dominates the density of the universe. Sometimes called the unbearable lightness of nothing. But the other thing about the cosmological constant is that cosmologists were quite used to the idea that there might have been a cosmological constant in the early universe. This is what's called inflation. Inflation says that at an early stage in the universe expands exponentially fast. And it expands exponentially fast because of the effect of a cosmological constant. Now, I won't go into the details of that. Maybe another speaker will do that. But basically, inflation theory solves a lot of observational problems. So it's very popular among cosmologists. But the point is that what had been discovered by these supernova observations is that there's still a cosmological constant even today. And that's what's causing the acceleration of the universe. Now, well, you might say, well, that's all right as a theory, but can you test it? And the remarkable thing is you can test it. Because if you actually, what inflation says is that there's the Big Bang on the right. Inflation is an exponentially expanding state of the universe. I mean, the universe is always expanding, but now it's expanding exponentially. And that's represented by this curve here. This is the scale of the universe. And then when you get to decoupling at 1 million years, inflation has generated these temperature fluctuations, which are seen in the microwave background, the cosmic background radiation. This is the same picture I showed you before, that was the WMAP satellite. And what's really remarkable is that you can analyze the nature of those fluctuations. those temperature fluctuations can be analysed as a function of angular scale. That's to say, what's the typical variation in temperature if you look at regions separated by a certain angular scale. So this is the temperature here, but in microkelvin, so it's a millionth of a degree. And this is the angular scale. And the point is, I won't go into the details, but there's a predicted pattern implied by the inflationary theory. And the data is described by the dots, and the pattern is described by the green line. And what's remarkable is that it actually fits the data exactly. And really this was remarkable because, you know, theorists had been talking about the predicted anisotropes, as they're called, for, you know, 20 years, ever since 1980. And yet when we then looked at the sky, we found exactly these fluctuations. It was really magical. And so some people say, Hawking used to say, this is the confirmation of inflation. Other people say can't quite go that far, but at least it's a remarkable triumph for the inflationary picture. So, as I say, these fluctuations predicted were actually measured. Now, so now I can depict the history of the universe in this modified Big Bang picture. So the universe starts on the left here, and the width of this black region is the size of the universe. So we start off with inflation, various key steps. I won't go through this except to say the helium era is the Big Bang nucleosynthesis. Then we have so-called dark ages. Nothing happens, I mean, until we actually have galaxies forming at about 1 billion years. And then eventually we form planets, stars and planets. And here are us looking back at 14 billion years. But the point is, there's two accelerating phases. Here is inflation, and here now we're accelerating now. Now, why is that? So try and keep this picture in mind. I mean, obviously I could give a longer talk about the precise history of the universe, but I don't want to do that now. So in terms of the predicted behavior, you remember in the old Friedman models, the universe either recollapses or expands forever. If there's a cosmological constant, it's going to expand forever. And what's more, it's going to expand exponentially fast. So it will expand even more. So that's one possible, in some sense, that's the most likely future that now awaits us, although there are variants on that. And I don't want to overwhelm you, but just what this dark cosmological constant is sometimes called dark energy, and it dominates the density of the universe. There's something like 70% of the energy of the universe is in the mass of the universe is in the dark energy. There is also cold dark matter, and that takes up about 25% of the universe's mass. And then there's the visible mass, which is about 5%. I'm not going to talk about the cold dark matter, but I just want to make sure you distinguish between the dark energy and the dark matter. The visible matter, which we all see and which we're made of, only makes up a tiny fraction, 5% at most of the mass of the universe. So, message 2. Message 2 is that the observable universe is a minuscule part of a larger physical reality. Why do I say that? Well, remember the cosmological constant was driving inflation. And in the inflationary picture, our universe is part of a bubble. This is one inflation, the simplest inflationary picture. It's part of a bubble. But and so here's this bubble. And our visible universe is just a little red patch here. It says 15 billion. It's probably 40 billion, but never mind. But the point is, also in this model, there should be other bubbles. So this is the sort of a simple inflationary model predicts a picture something like this. Inflation, remember, goes back to 1980. It's quite old. And so in some sense, there could be many different Big Bangs. Now, obviously, this is speculative. We can't see these other bubbles. But the point is the observable universe is a minuscule part of a larger physical reality. And basically, the idea is, in a way, this isn't too surprising. If physics can we're trying to explain the Big Bang by physics. I mean, it's all very well saying it starts off with the universe starts off with a singularity, but ultimately physics wants to explain that. And so if physics is going to explain one Big Bang, presumably in principle it can produce many Big Bangs. So we shouldn't be too surprised if we predict the existence of other universes. In some sense, qualitatively speaking, it's rather to be expected. But what I want to stress at this point is that there are actually many different multiverse proposals, and probably other speakers will address some of these, but I'm going to just briefly say what they are. The one I've spoken about so far is sometimes called eternal inflation, and this is just another picture, comes of Lindo, a bit like the one you saw before. And in this case, you've sort of got many universes in space. And actually, you know, there's a lovely picture. I think these talks are meant to be sort of cross-cultural. People are not only going to be talking about the multiverse from a scientific perspective. So here's some lovely pictures. The idea of inflation has inspired some rather beautiful pictures. So here are some artistic impressions of eternal inflation, which may not convey the science, but certainly, you know, convey the beauty of some of these ideas. The other idea, which is quite an old idea, I've said our universe is expanding, but eventually it could, if the universe was closed, remember, in the old Friedman model, it will stop expanding and it would recollapse. And then, if it recollapses, it could bounce into another expansion phase. So you could imagine having cycles. Now, of course, I said that in the inflationary model, the universe may expand forever. So it's not clear that a cyclic model is compatible with inflation, but at least this is an alternative model. And the question is, at what density do you have to bounce? It doesn't necessarily have to be a very high density. It could bounce as you go back in time. For example, our universe could have bounced at a relatively low density. So you've got this sort of picture here where you can see the galaxies. Now, we don't know this happened, but it's one of the possible models of the universe, that before our Big Bang there was another collapsing universe, and after our big recollapse there will be another expanding universe. So this is a sort of picture we have. But this is, if you like, is many universes in time rather than many universes in space. Now, recently you might have heard Roger Penrose talking a lot about his conformal cyclic model. That's a little bit more complicated, but because the point is that his universe, I'll give a slightly more, well, this is from one of Roger's famous slides, but this is a slightly more, I suppose, precise picture. In his conformal cyclic model, it's a little bit different from the cyclic model I showed you before, because you've got they're stupendously long. Each of these phases goes on for 10 to the 100 years, whereas the cycles before might have been just 10 to the 15 years or something. So they're enormously long, and this is a bit too technical to go into, but in some sense each of the universes expands rather like in the lambda CDM model, expands forever, but at some stage it develops into a Big Bang. So this infinite expansion at late time turns into a Big Bang for the next cycle. So this is called the conformal cyclic model. Not very popular among cosmologists, but another example of how you can have many universes in time. Another entirely different idea is that there could be a fifth dimension. We don't see the fifth dimension because we're trapped on this four-dimensional slice, which is called the brain. But some people think that there could actually be many universes spread out in this fifth dimension. I think this comes from the Metro newspaper, which certainly James probably reads, being a Londoner. Again, it's a slice of bread. It looks as though it's gone mouldy, but anyway, it's just another way of envisaging the brain, these many brains, this particular version. And I might also say, though, at this point, not everybody believes in the inflationary model. People like Paul Steinhardt and Neil Turek, they believe what's called the ekpyrotic model. They think that you do have a cyclic model, but the cycles are because you've got two brains which collide. And so it's the collisions of the brains which is supposed to produce a cyclic model. So in some sense, this is a mixture of the cyclic model and the brain model. Now, obviously, we don't know for sure this fifth dimension exists, and we can't demonstrate observationally that these other brains are there, but nevertheless, it's a theoretical possibility because it's predicted by some theories. And another very famous version of the multiverse is the many worlds interpretation of quantum mechanics, which says in quantum mechanics, a system is described by a wave function, and the idea is that when you make an observation, the wave function collapses. And there's a huge debate as to how you interpret the collapse of the wave function. I know Basil Heil is in the audience, and he's a great expert on that. But physicists are divided about the interpretation. But one of the interpretations is that the universe splits every time the wave function collapses, and this is called the many worlds picture of Hugh Everett. So in this case, you've got a quantum splitting. And so you've got many worlds, but these are many worlds which don't come out of cosmology, they come out of quantum mechanics. And I think tomorrow Paul Tappenden is going to give a talk on this very topic. Now, I've really been talking about how the multiverse is predicted by particle physics. But actually, sorry, let me rephrase that. I've been talking about how the multiverse is predicted by cosmology. But there are also predictions from particle physics. Now, these are a little bit technical. Many of them relate to the idea that you can have extra dimensions beyond the 3 dimensions of space and the 1 dimension of time. I might talk about this later in my second lecture. We think of the universe as 4-dimensional, but Kaluza-Klein in the 1920s suggested it could be 5-dimensional because the 5th dimension would then allow you to have a geometrical interpretation of electromagnetism as well as relativity. And then when superstring theory came along in the 1980s to describe the other interactions, this was meant to be, a great final theory of physics, then you needed 10 dimensions. So you would have the 4 large dimensions, but you'd have 6 extra dimensions, which are sort of wrapped up very small so you don't see them. There were actually a variety of different versions of superstring theory, but then in 1995, we had M theory, which combines these different versions into an 11-dimensional theory. Now, I don't want to get into the details of that. Clearly, if you're not a physicist, which I understand most of you aren't, it's a bit hard thinking in terms of 11 dimensions. But I just want to get across the idea that that you've got these theories of physics, which in some sense are respectable theories in the sense that famous physicists think about them. And in M theory, for example, a lot depends upon the geometry of the compactified dimensions, and the image which I have on the front of my book, for example, corresponds to what's called a Calabi-Yau space, which is a description of the geometry of these internal dimensions. I don't want to get any more into M theory now, but the point is there's something called string landscape. This diagram, I'm afraid, is a little bit complicated, but it's taken from a Scientific American article by Busso and Polchinski. But the idea is that in M theory, you have different vacuum states, and each vacuum state corresponds to a different value of the cosmological constant. And also, in theory, would be able to predict all the physical constants of things. Now, at one stage, it was hoped that M theory would give you a unique solution. But that didn't turn out to be the case. And now it's been argued by these people that there could be something like 10 to the 500 vacuum states. Okay, in other words, universes with different values of cosmological constants. So this is another multiverse theory because it's universes with different values of the cosmological constant. So why are we in the one which actually we observe? And I'll come back to that later. And the final version of the multiverse is a bit complicated, but it relates to the many worlds picture of quantum mechanics. The question is, what happens at the Big Bang singularity? Hawking was the person who, he showed that there was a singularity at the beginning of the universe. And Penrose, of course, showed us a singularity in the center of black holes. But that doesn't mean physics breaks down, it means relativity theory breaks down. And in the last 20 years of his life, he was working on quantum cosmology, which is the attempt to try and understand what happens at that singularity. And in quantum cosmology, you're sort of applying the idea of a quantum wave function to the whole universe. Now, you remember I showed this picture of the Big Bang, which was one of these pictures, but in quantum cosmology, in some sense, what happens is you have a superposition of all different universes. This is a picture from Max Tegmark. And so quantum cosmology gives you a superposition of cosmological states, and at some point, our observable universe has to, of course, solidify, if you like. And I have to say, most people, most physicists, don't really like the Everett's many worlds picture. However, quantum cosmology, which is regarded as quite respectable, does actually depend upon it. And I would say, I don't know what Paul's going to say, but I would say, if there is any evidence for the many worlds picture, I mean, sociologically, it probably comes from the popularity of quantum cosmology in some quarters. Well, so just to summarize, this is a slide from Max Tegmark. Just to summarize then, there are different types of multiverse. There are the different Hubble volumes. They're the regions beyond the horizon, which definitely exist. Then you have different, in the inflationary model, post-inflationary regions. This is what's type 2. We don't know they exist. We can't observe them, but they are predicted. And then we've got the quantum many worlds, which he calls level 3. He also has what he calls level 4, and that's, to me, even more extreme. You see, you could imagine worlds where the laws of physics are completely different, the mathematics is completely different. And so you could say, well, which of those universes could have life? And so these correspond to different mathematical structures. It's sort of based on the idea that anything you can think of must exist. You know, anything which physics allows would exist. Now, I personally, as you go from level 1 to 4, you should become more and more skeptical. You have to believe in 1. I personally tend to believe in 2. 3 is questionable. I'm not keen on 4. I think Max has gone a bit beyond the fringe, but some people believe that. Not beyond the fringe, sorry, beyond the pale. Now, so message 3. Cosmology and particle physics suggests that there could be many other universes. And just to summarize, cosmology gives us the cyclic model, the eternal inflation and the colliding brains, and particle physics gives quantum many worlds, string landscape, and quantum cosmology. So I hope obviously any of these models could be discussed in more detail, but I've tried not to get too technical. But the point I'm trying to get across is that there are actually, the idea of a multiverse arises in many different contexts. But now I want to get on to the Anthropic. By the way, just in case you're wondering, I'm assuming I can go on talking for about another 1 hour, not another 1 hour, another maybe 20 minutes or so. Just in
Sure,
case.
of course.
Yeah. So now let's get on to the anthropocentric, the Anthropic principle. Now, not all physicists like the multiverse. The number of physicists who like the Anthropic principle is fewer, because this is even more controversial. But it's one of my own favorite subjects. Now, the anthropocentric view says man is, sorry, that should say human, not man. I keep, this is an old slide. Nowadays, I must say human. Men and women are central to the universe. Well, of course, we know that view died as soon as we went to the heliocentric view, but nevertheless, that's what we started with. So there's a little image of that, which I showed at the beginning. And after Newton came along with his Principia, for several centuries, the mechanistic view prevailed. And the mechanistic view says, well, the universe sort of exists independent of our awareness of it. So we're more or less irrelevant. I mean, we're passive observers. So, you know, energy conservation applies. It doesn't matter if anyone's watching it or not. So that's the mechanistic view. Obviously, the advent of quantum theory has somewhat changed the view, because the whole question of what you mean by an observer comes in. But at least that was the classical perspective. were irrelevant. But then we got the, and that's my image of the mechanistic view, sort of mesh of rods and things and clocks. And then came the anthropic view. And when I say then, I'm talking really about from about the 1960s. And the idea of the anthropic view is that some features of the universe are explained, in inverted commas, by the requirement that life and mind should arise. In other words, by the fact that we should be here. And this is the so-called the anthropic fine-tunings, which I'm going to talk about. And so I represent that by putting an I there. I representing us, consciousness in some sense, the observer. Now, I don't really like that interpretation. To me, I mean, the anthropic is a terrible word. It's the Greek word for man or human. I tend to see these fine-tuning as to do with complexity. I might say more about that later. The idea is that the Big Bang should lead to increasing order and complexity, culminating in mind. So you see, one of the reasons the anthropic principle gets such bad press is because of the word anthropic. Because the very word anthropic is very anthropocentric, because it implies it's something to do with us. It makes it sound as though the world was created for us, which sounds very theological. To me, these fine-tunings are to do with complexity, and I would call it the complexity principle, but it's a bit late now because we're stuck with this word. Now, the great work on this subject was the book by Barrow and Tipler in 1986 called The Anthropic Principle. John Barrow was a friend of mine. We used to work. I call him my cosmological twin, and we were great friends. And very sadly, he died just nearly a year ago in next September. And so this was a really important book, but also John was a really important person in this field. So I sort of I'd like to dedicate this lecture to his memory, if that's in order. Now, more recently, there's been a book on fine-tuning, which has come out in 2020 called Fine-Tuning in the Physical Universe. I have a chapter in that book where I talk about some of these things in greater detail, but that's just for people who want to read more about it. Now, the first thing you should bear in mind is that there are different types of tuning. First of all, straightforward physics does predict natural coincidences between scales of structure. For example, the size of a human being is a geometric mean of the Planck scale, the smallest scale you can ever have, 10 to the minus 33 centimeters in the universe. And you might think that's remarkable, but actually it's a simple prediction of physics. It's a surprise because you might not think that, but it's a prediction. But then there is what you might call the weak anthropic principle, and this says there's a selection effect for when and where observers exist. And in some sense, that is non-controversial. And I'm going to give you an example of that in a moment, because it's a necessary consequence of our existence, and it's perfectly logical. The really controversial concept is that there are fine-tunings between the constants themselves, which are needed for observers but aren't predicted by physics. And this is called the strong anthropic principle. Now, in some sense, if you have a multiverse, the strong anthropic principle becomes an aspect of the weak anthropic principle, because it just says there are many universes. By a selection effect, we are necessarily in one of the universes where we can exist. So that's where the link comes in. Now, I'm going to cut this. This was my first paper on this subject was in 1979 with Martin Rees. It was a paper which appeared in Nature. And it got some attention because it was the first paper which put all these arguments together. And so, but also precisely because of the word anthropic principle, we came in for quite a lot of flack. There were a lot of people who didn't like, well, actually, most people liked the part of the paper dealing with the structure of the physical world. but they didn't. A lot of people didn't like the idea of the anthropic principle. Well, that's what I'm going to talk about now. I'm going to miss the next slide. So let me give you an example of why the universe is as big as it is. This is the weak anthropic argument. And I mentioned the universe began with a Big Bang 14 billion years ago. So the size of the universe is roughly 10 billion light years. So you can ask the question, why is it that big? Well, the mechanistic view is simply that the Big Bang was 10 to the 10th years ago. So the size of the observable universe is 10 to the 10th light years. And there's no particular reason for it. But the anthropic argument came from Bob Dicke, and this was in the 1960s. He says life requires heavy elements, such as carbon, and those heavy elements are made in stars, and then the star explodes and disseminates the heavy elements through the universe. Now, this means there can be no life before a star has completed its evolution, which roughly takes 10 to the 10th years. On the other hand, if you wait much longer than 10 to the 10th years, all the stars will have burnt out and we probably need life to exist. And therefore, this is telling us that life can only be around at around 10 to the 10th years after the Big Bang. So the size of the universe is roughly 10 to the 10th light years. Now, this isn't saying that the universe doesn't exist apart from this time. It's just saying we wouldn't be here to speculate about it. And so that's what's called a weak anthropic argument, because it's just as you would say life has to be near a star, we would say that life, which is a selection effect in time, we would say that life has to exist at a selection effect in space. Similarly, life has to exist round about 10 billion years, which is a selection effect in time. So I don't think that's very controversial. James, can I check you're there, because all the pictures have disappeared?
Yes, I'm here. Hi.
That's great. That's fine. I don't know why the pictures have disappeared, but it doesn't matter as long as you can see my pictures. Now, what are these fine-tunings? There are four forces in nature: gravity, the weak force, the electric force, and the strong force. And they all have a strength, which is described by a dimensionless coupling constant. So, for example, for gravity, that's very small. It's about 10 to the minus 40. For the weak force, it's 10 to the minus 10. For the electric force, it's 10 to the minus 2. The strong force is about 10. Sorry, I'm showing an equation here, but the point is, those are the relative strengths of the forces. So, for example, the gravitational force between two protons is much weaker than the electric force, because by a factor of roughly 10 to the 38. Now, but the question is, will the final theory of physics explain these values? Now, remember, we don't have the final theory of physics. M theory doesn't do this yet. But the question is, are these values going to be predicted uniquely, or are they, in some sense, contingent? In other words, will the final theory allow a range of possibilities? Well, there are some coupling constants which seem to be relationship between these constants which seem to be required. For example, the argument's too technical, but in order to have stars and planets, you need to have alpha G being the 20th power of alpha E. And you can see that's right, because the 20th power of 10 to the minus 2 is 10 to the minus 40. In order to have, I can't give you the argument for that, it's too technical, but it basically involves having what we call, you've got two types of stars. In one type of star, the heat gets transported by radiative effects from the core to the surface, and in the other type of star, it's converted by convective effects. And you need both types of stars, and that only happens because of this relationship. Now, supernova, They're required because, remember, when a supernova explodes, it disseminates all the heavy elements that are needed for life. But they only explode because of the weak force is finely balanced against the gravitational force. When a supernova forms, it gets very hot, it generates neutrinos. The neutrinos interact by the weak interactions with the envelope of the star. If the weak force was too strong, they would never get out of the star. If it was too weak, they would just stream out of the surface. But if it's just right, it blows off the surface. And that requires alpha G is the fourth power of alpha W, which again is the correct, because the fourth power of alpha 10 to the minus 10 is 10 to the minus 40. So the point is, these relationships are required for life, but they're not explained by physics. And oh, here's some pictures. This is just where stars are forming, and this requires this relationship here. And this is a supernova, and this requires the relationship alpha G is alpha W to the fourth. I'm showing pictures instead of giving you the technicalities of the argument. There are also constraints that come from chemistry. Now, maybe this is a little bit too technical, but if the strong force was a little bit stronger, all the protons would go into diprotons at Big Bang nucleosynthesis, and then you wouldn't have any hydrogen burning stars. If it was bigger by 10%, all the protons would go into nuclei of unlimited size, and you would never have any interesting chemistry. And you need chemistry, of course, an interesting range of elements for life. On the other hand, if alpha S was decreased by 5%, all the deuterons in the universe would be unbound, and you would only have hydrogen. And again, you would not have any interesting chemistry. This is I think this is probably a little bit too technical. I'm going to actually skip this. The point is that there is fine tuning between the mass of the electron and the mass of the proton, and the difference between the neutron and the proton mass. But let me skip that. It's getting a little bit technical, and I'm getting a bit low on time. Another famous coincidence involved what's called the triple alpha coincidence. We need carbon, and carbon is made in stars. First two helium atoms called alpha particles, they merge to form a beryllium atom, and then the beryllium atom merges with another alpha particle to form the carbon. But the trouble is that wouldn't normally happen because the beryllium decays. And the only reason you form carbon is because there's a resonance which allows in other words, an increased interaction strength which allows the carbon to form. And Fred Hoyle realized this, and it's called the triple alpha reaction, and he predicted that there had to be this resonance, which was then looked for and found. So this might be regarded as an anthropic prediction. And this is what Fred Hoyle regarded as evidence that the universe was a put-up job. I hope this is not getting too technical, but at least I'm trying to get across just the idea of why there is an unexplained coincidence there. Perhaps the most dramatic of all the anthropic tunings is called the cosmological, is associated with the cosmological constant. Do you remember I said that the cosmological, in the string landscape picture, you could have any value at all for the cosmological constant. But the cosmological constant today, the energy density is roughly comparable to the energy density of the ordinary matter. And that is far, far smaller than you would expect, because naively you would expect the cosmological constant to be much bigger. And so the question is, why do we live in a universe where it's so much smaller than expected? And one of the arguments for that was given by Weinberg, and he said that if the cosmological constant were any bigger, galaxies couldn't form, because the cosmological constant is a repulsive effect which stops galaxies forming. And so Weinberg was a very famous physicist who sadly only died a few months ago. He was one of the people who became a supporter of the anthropic principle because of this coincidence. And a lot of people think that this is the best explanation of this is to say that we have to be in one of the string landscape universes where the cosmological constant is surprisingly small. Martin Rees has written a book called Just Six Numbers, where he summarizes a number of other fine tunings which are required for us to exist. And I'm not going to go through those now. Martin is one of the strong advocates of the anthropic principle, and indeed we wrote our first paper together way back in 1979. So I'm not going to go through all of these now, but if you want to ask questions about that, I can do that later. But now we're coming to the end now. Let's now ask, though, what is the interpretation of the anthropic principle? And broadly speaking, there are three different types of interpretation. The first is to say, well, maybe God created the universe. You can imagine that there's a space with all the constants of physics, and God chooses the constants of physics so that we can arise. Now, not surprisingly, most physicists don't like this idea. And indeed, this is why the anthropic principle was so unpopular when I wrote my paper with Martin in 1979. It somehow smelt of God, and physicists by and large don't like, I won't say they don't like God, they don't like theology. They like to keep physics separate from theology. There was another view which was a bit more related to physics, I would say, but might be described as a metaphysical rather than physical view. One of the possible interpretations of the collapse of the wave function is that consciousness itself collapsed the wave function. And so John Wheeler had this idea, well, maybe we have the universe, which evolves galaxies and stars, planets and people, and then the people become conscious. And then by observing the universe, and indeed looking at the beginning of the universe, in some sense, this brings the universe into being. It's like a closed circuit. But most physicists didn't like this idea because, first of all, the idea that consciousness collapses the wave function is not the mainstream view. It's just one of many views of interpretations of the collapse of the wave function. And clearly this is rather philosophical for most people. So I think most physicists would prefer this to invoking God, but they would still not think it was proper physics. So then we come to the multiverse. And the point about the multiverse is that if in each of these multiverses you have different values of the constants, then by a simple selection effect, we're going to be in one of the universes which has got the values required. So that, if you like, produces an explanation of the anthropic tunings. It basically reduces the strong anthropic principle to the weak anthropic principle. And many physicists like this because it removes the need for God. But I have to say that there's another set of physicists who regard the multiverse as just as metaphysical as God, and just as mysterious. So I shouldn't give you the impression that all cosmologists believe in the multiverse. But so how do we decide? I love this picture of Einstein in his dressing gown because I like to work in my dressing gown. Einstein says, what really interests me is whether God had any choice in the creation of the world. And the point is this, the status of the anthropic principle and the multiverse all depends on this final theory of physics, which remember we haven't got yet. Now, you've got two options. Either the final theory of physics, if it may determine all the parameters uniquely. And in that case, there's no role for anthropic reasoning. There can be only one universe, or if there are other universes, they're all having the same constant. So there's no role at all for the anthropic principle. However, if you're allowed to have universes with different values for the parameters as a result of, different symmetry breakings, compactifications of extra dimensions, then of course you're in the scenario where you simply have a selection effect which says the parameters in our universe should be typical of those the anthropically allowed subset. And so that's all it comes down to. And we don't know what the final theory is. As I said, originally it was hoped that M theory would give us a unique theory. Now it doesn't seem to give us a unique theory. It seems to give us 10 to the 500. But we might hope that there could still be another theory that does. But even if there is, it will be remarkable that the values of the constants predicted by the final theory are just the values required for life to arise. So the question is, what actually counts as an observer? If it is a selection effect, what counts as an observer? As I said, anthropos is the Greek word for man, but this is clearly nothing to do with humans in particular. I mean, do you have to be a human being? That would be very anthropocentric. But can a mouse collapse the wave function? Can a robot collapse the wave function? Can a photon collapse the wave function? Sorry, Tegmark isn't the mouse. Tegmark, I got this slide from Tegmark, so I wasn't implying Tegmark was a mouse. But that turns out to be, you know, the really crucial question. And there are different views. Some people say, well, it's consciousness is fundamental. Some people say, no, it's life. Some people say, or maybe it's just complexity. And I actually think complexity is crucial because, you see, the idea is that during the Big Bang, if you go through the history of the Big Bang, which I showed a slide about, there are various stages where you form more complex things. So at some point you form the quarks into nuclei. Then after, at a later stage, you start forming atoms and molecules. When you start forming galaxies and stars and planets, you start getting biomolecules and life. And then in some sense, you end up with brains and consciousness. But the point is, what you see is that the Big Bang involves the development of complexity. It's what I call the pyramid of complexity. But this only happens because you have the fine tunings. The various points in the history which allow you to build up complexity do depend upon these fine tunings, some of which I referred to. So my fourth message is the multiverse naturally explains the fine tunings. Now, if you don't believe in the fine tunings, you might say, well, fine, I don't believe in the multiverse. But if you do take the fine tuning seriously, I do think the multiverse is the most natural explanation. I prefer that to God, put it that way. Although I have to say, it doesn't disprove the God, because if God can create one universe, he can clearly create many. But at least you're not forced to invoke God. So let me just, coming to the end now, but let me just give you some different flavors for how people feel. Here is a flavor, here is a quote from Freeman Dyson. I do not feel like an alien in this universe. The more I examine the universe and examine the details of its architecture, the more evidence I find that the universe in some sense must have known we were coming. So he's in favor. On the other hand, here's Heinz Pagels. The influence on the anthropic principle on contemporary cosmological has been sterile. It has explained nothing and has even had a negative influence. I would vote for rejecting the anthropic principle as needless clutter in the conceptual repertoire of science. And Brandon Carter, who coined the word anthropic, he takes a middle way. The anthropic principle is a middle ground between the primitive anthropocentrism of the pre-Copernican age and the equally unjustifiable antithesis that no place or time in the universe can be privileged in any way. Now, when we first wrote our papers in the 1979, I would say that the Heinz-Pagel view was the more popular one. Now I would say, especially with the multiverse, most people would adapt Brandon Carter's view. At least I hope so, because obviously I think it's clear I'm somebody who favours that view. Now, I've got a whole list of objections to the anthropic principle. I'm not going to discuss those. We're running out of time, and you might want to actually talk about that in the discussion period. The crucial question, which I'm going to end on in my last 5 minutes, is the observable universe, is the unobservable universe part of science? Now, one of the problems here is that Martin Rees calls the slippery slope argument. With our telescopes, there's a distance, a greatest distance to which we can see. You know, because obviously the further the object is, the lower the luminosity. So there's a technical horizon, but there's also there's a speed of light horizon, which is the greatest distance light can travel. That's what I call the horizon size of the universe. You can't see beyond that. But in these accelerating models, there's also a part of the region, there's a region of the universe you'll never see beyond ever. this is a feature of the accelerating universe. And so this is called a slippery slope, because all of these horizons, you go from one horizon to the other. But it will be crazy to say that the universe doesn't exist beyond these horizons, because these are natural horizons that do exist. So, but even in this context, which I was saying, the context where it's what Tegmark's level 1, you have to say, you know, the universe does exist, but is it part of science? You know, rather like the philosopher Kant said, well, there may be something beyond the solar system, but it's not part of science. We've got this analogous question here. Well, it depends what you mean by science. You see, you might say, well, science is all to do with experimentation. But you can't do experiments on stars and galaxies. So you might say, well, okay, but astronomers at least can look at millions of stars and millions of galaxies. So it's like doing an experiment. But when you're doing cosmology, there's only one universe. So that's not a very good criteria, because everyone would accept that cosmology is part of science now. Some people say, well, you have to be able to observe something for it to be part of science. But that's not true, because, you know, you can never see inside a black hole. You can never see quarks, but they're still part of the theory of physics, because the theory can be tested in other ways, and the same theory which is testable makes these predictions. And it's the same with the multiverse. Maybe the theory, you can't see the other universes, but maybe you can test the theory which predicts their existence. And then maybe the main argument is, well, how can you ever falsify? This is the Popper idea that science has to involve falsification. And that's a more subtle objection. I would only say that Popper is a little bit out of fashion now. Now, I've had many debates with George Ellis about this. We're good friends, but we've had slightly different views. George, but it's not that he doesn't believe in the multiverse. It's not that he disbelieves in the multiverse. He just doesn't think it's part of science. He thinks it's part of philosophy. And George is interested in philosophy and indeed theology. He just doesn't think it's part of science. And he says the multiverse cannot make any testable predictions because it can explain anything at all. And then he says, can one maintain one has a genuine scientific theory when direct and indeed indirect tests of the theory are impossible? Well, I defend it. I mean, we've got articles on this. I defend it. I had a beard in those days. Sorry, that's irrelevant. But anyway, one needs some degree of falsifiability. I agree with that. But the question is how much and how soon. And the other point I make is that the multiverse is part of science if it's predicted by a physical theory. Well, I mean, it is predicted by a physical theory. I pointed out, for example, it's predicted by M theory. But the troll is we still don't have any confirmation of M theory. And there are these famous books, for example, arguing that M theory is untestable. It should be regarded as maths rather than physics. The book by Peter Voigt, Not Even Wrong, and by Lee Smolin, The Trouble with Physics. So, you know, this is contentious too, because you could say M theory is just as untestable at the moment as the multiverse. And of course, it all depends on what you mean by science. The general concept of science is you have an idea which makes predictions, you look for the observations which either confirm or modify the theory and things like that. But the really crucial question to me is, what is the timescale of each of these steps? You say, it's all very well to say M theory is maths rather than physics, because after 30 years, we still haven't solved all the equations. But, you know, it might take 100 years. And when we've solved all the equations and when we've managed to test it through even higher energy accelerators, then it would become legitimate science or legitimate physics. So really the question is, are you going to say it's not science just because you're going to have to wait more than a PhD period to solve it? So I agree one needs a degree of falsifiability, but the question is how much and how soon. And in fact, I compromise with George by saying that the multiverse is what I call metacosmology. It's a sort of midway state between cosmology and philosophy. Until we have the empirical data, it isn't proper science. But nevertheless, once the empirical data comes or the solution of the equations comes, it becomes a proper science. So I'm sorry, I'm going to cut this. I want to come to an end now. it has been claimed that there is evidence for the multiverse, but it is controversial. I mean, people have looked for evidence that, you know, we might have bumped into other universes at an earlier stage through scars on the microwave sky. People have claimed that there's unexplained flows of clusters of galaxies which is produced by something beyond the horizon. But I don't want to get into that idea now because it's controversial. I mean, I just quote George Stathiou, such ideas may sound wacky now, just like the Big Bang Theory did 3 generations ago, but then we got evidence and it changed the whole way we think about the universe. And remember, that was one of the themes I was discussing in the early first part of my talk, that cosmology is now a respectable branch of physics. But it wasn't always like that. It only became respectable over many decades as we got the evidence. And I think the same is true of the multiverse. It's not yet respectable. It's now metacosmology, if you like. But once the evidence comes, I think it will become legitimate. I just want to end with a quote from Steven Weinberg. My final message, the nature of legitimate science changes. Steve Weinberg took part in the 3rd meeting, and he wrote a very nice chapter for the book. We usually mark advances in the history of science by what we learn about nature, but at certain moments the most important thing is what, sorry, I have to move this, I can't lose, is what we discover about science itself. These discoveries lead to changes in how we score our work in what we consider to be an acceptable theory. As you know, Steven Weinberg died a few months ago, but I thought this was a very important result, that the nature of science does change. He had another quote, which I'll describe. I found a report of a discussion at a conference at Stanford at which Martin Rees said that he was sufficiently confident about the multiverse to bet his life's dog on it, while Andre Linde said he would bet his own life. As for me, I have just enough confidence about the multiverse to bet the lives of both Andre Linde and Martin Rees's dog. Martin Rees's dog sadly has died, and sadly so has Stephen, but Andre Linde is still going strong. And actually, my very final slide is the actual proof of the multiverse. I thought I should end up on a positive note by giving you the proof. This was when my wife is Japanese, and on a visit to Japan, we visited a field which was full of flowers, and the flowers are called cosmos flowers. And so I thought I would end on this picture. I'm standing among the cosmos flowers, which, if you like, is the observational evidence that there are many other cosmoses. And on that joking note, I will end. Sorry, I've been 90 minutes, so I hope I've left time for questions. Thank you.
Thank you so much, Bernard, for that. That was a really fantastic presentation you gave there. And thank you so much for explaining all these very difficult concepts in a very clear and simple way. So thank you so much for that. Okay. Just before we move on to Q&A, I'd just like to invite the chair of this event, director of the Carr Center, Shantana Sabadini, to see if he had any comments or questions for what has just been said. Bernard, can I just ask to stop screen sharing?
Yes, of course.
Thank you. Thank you.
There we go.
So yes, hi Shantana.
Hello, James. Bernard, very, very, very much thank you for a wonderful lecture. So rich and so profound on many levels, physics and beyond. I'm very happy to have the privilege as director to ask you questions right before everybody else.
Well, my pleasure to answer them, I hope.
Yeah, two questions. One is in this slide you showed about quantum cosmology.
Yeah.
The different evolutions of the wave function of the universe are shown. And in this various evolutions, an eye appears on the other side.
Yes.
Would that eye be an observer? Would it be conscious in a more general sense? What could be, how could
Yeah.
we
When I use the eye was just being used as a symbol for consciousness for an observer. I mean, the point about quantum cosmology, because the picture, the eye appeared there as well, is that, I mean, Stephen Hawking, of course, who spent the last 20 years of his life working on quantum cosmology, that's why Stephen was a supporter of the multiverse. He was, he was one of the eminent physicists who supported the multiverse, but because it was to him the only way he could interpret quantum cosmology. Now, in quantum cosmology, the idea is that you've got many universes which coexist. But then we necessarily, again, because we're observers, we have to exist in we have to be in one of the universes where the constants are right. And in quantum cosmology, at some point, you've got to end up being in a classical universe. So you end up in one of these universes. But that's why it relates to the Everett's many worlds interpretation. I mean, I think it's rather hard to interpret quantum cosmology without the Everett's many worlds interpretation. But it's a little bit, and so within that picture, for example, Thomas Hertog and Stephen wrote many papers explaining how you would naturally, you would have some selection effect on the fact that we as observers are here now, and that is going to select the possible versions, the possible universes that come out of quantum cosmology. So in a way, it's a little bit like the Wheeler picture, where but because in Stephen's approach, in some sense, you have a retroactive effect in that the observer is actually creating the past, which of course sounds rather counterintuitive, but that's the sort of idea that does arise rather naturally in that picture. So within the quantum cosmology picture, you say there are all these different universes, but necessarily we are in one of the universes which will allow observers. And for example, the universes, all those universes which have too high a cosmological constant, they would recollapse to, they would never form galaxies, or maybe the universes would recollapse too soon. So basically, it's natural within that picture to say that the existence of observers does impose a selection effect on which of them the quantum cosmological universes you're in.
Right. And thank you. And I'm very convinced by that argument. It seems to me that explaining these coincidences is a key element.
Yes, but bear in mind, though, that not everyone does believe quantum cosmology. I mean, Stephen has quite a big group.
I wanted to ask you about that. If you take the other point of view, which I consider much more natural, but of, let's say, decoherence,
yes,
rather than the Everett multiple universes, how would the argument shift? Or
well, I mean, one does interpret the quantum cosmology. One talks about decoherence, and how in explaining why we're in our particular universe. I mean, are you asking about are you contrasting that with the actual Everett picture itself? Because I mean, it's not clear how the Everett picture, for example, if you take the Everett picture in its own terms, that doesn't necessarily allow the constants to vary, for example. I mean, because when the universe splits in the Everett picture, you don't have the concept that the constants are changing, the fundamental constants are changing. Normally in the standard Everett picture, the constants are fixed in all the different universes, in all the different branches. So I mean, that's why I'm, in its own terms, I'm not so fond of the Everett picture. I'm sure that actually we're going to look at this tomorrow. But I mean, so I'm not sure I've really answered your question properly, Shantino. So, are you asking me about many worlds?
You're guiding me to formulate my question more precisely. Say, there's one form of decoherence in which it's based on the idea of an equivalence between, let's say, the classical appearance of the world and the quantum, takes at face value quantum physics and the evolution of the wave function.
Yes.
But includes the equivalence of that state under appropriate circumstances with a classical picture.
Right. So you're not referring here to quantum cosmology in particular. You're just talking about normal collapse of the wave function. Yeah. So yes. So what I was saying is that I mean that's a more tricky. I'm sure that in fact we'll hear more about that from tomorrow in the lecture by Paul. So I mean, one of the problems is I've talked about the different versions of the multiverse, and you sort of can't have them all. I mean, in other words, if you want a multiverse which comes from, you know, inflation, that's in some sense that was the most natural multiverse. The question is, well, how does that multiverse relate to the many worlds multiverse, which was what Tegmark called level 3? And it's not completely clear. Some people have tried to relate these, you know, because in some sense, but it's a complicated question, and when you say, in some sense, there could be, it gets complicated if you're going to believe in both the inflationary universes and the Everett universes, let alone the, you know, the level 4. So it is a complicated question, and I mean I don't know what the answer is. It becomes, in some sense, it would be cleaner if there was only one multiverse. But once, I mean, and really it could turn out that the quantum multiverse is in some sense a red herring from the point of view of the fine tunings, and I'm sure some of the other speakers are going to focus on this. In some sense, the quantum multiverse, from the perspective of these lectures, is the most interesting. But nevertheless, in terms of explaining the fine tunings, it's not clear that the quantum universe is going to be, you know, the most important. But on the other hand, it's clear that the final theory of physics, which is going to amalgamate relativity theory and quantum theory, ultimately that involves quantum theory. So it's quite clear that the ultimate resolution of this, in other words, you remember I said that whether we have a multiverse is going to depend on the final theory of physics and whether it determines the constants uniquely. That final theory of physics is going to be a theory which marries together relativity theory and quantum theory. And therefore, it's clear that quantum theory itself and our interpretation of quantum theory must have some, you know, vital relevance to this question of the multiverse. But I don't know whether the Everett multiverse will be part of that picture, because that seems to be in some sense, you know, it's not the most popular view, and I would think it was rather inessential. But when we have the final theory, we will probably, presumably, the final theory of physics is going to tell us whether Everett's many worlds make sense.
Thank you, Bernard. And if let me.
Wait, can I put the light on? I'm in the dark at the moment. I mean, intellectually and physically. So let me just put this. Okay. I hope people can see me better now.
Here in Andalusia, where I am, there's still a bit of light.
Yes. Yeah.
So if I can just take advantage even more of my privilege of asking questions to everybody else, let me ask you about one argument that has been given in favor of multiple universes, I think by Carlo Rovelli, amongst others, is based on entropy, on the notion of that the initial condition must have been like very special in terms of very low entropy to justify the arrow of time.
Yes.
Would you include that argument in favor of multiverse?
Well, this comes into brings in the whole question of the arrow of time. Of course, the normal question is, how does the second law of thermodynamics arise? You know, why does entropy increase? And the normal answer given is it increases because the universe started in a very special state, a very special low entropy state. And this, of course, is something which Roger Penrose also always emphasizes. And therefore, for our own universe, it's clear that the universe did start in a very special state. In other words, a very smooth state. And so the question you're really asking is, when we consider these other big bangs, are all these big bangs also going to start in a very special state? In other words, like the simple Friedmann model, or should we allow more general models which don't have low entropy? And of course, we don't really know the answer to that question. It's clearly the direction of the. I think what is really fundamental is the arrow of time,
Yeah.
and the passage of time. And as I'm going to say in my next lecture, we don't actually understand the passage of time at all, because the passage of time. Sorry, I don't think that was a question, but I'll just wait for Shantina to come back. So Shantina, the passage of time which we experience is crucial, but it's not explained by standard physics. In standard physics, in relativity theory, there is no passage of time, because past, present, and future coexist. And therefore, but the passage, so the question is, how does the passage of time relate to the physical arrow of time? And to me, this is linking up actually with the whole issue of consciousness, because I left it open. What is the fine tuning actually for? I mean, I said it's for complexity, but at the end of the day, you've got to say, well, are we fine tuning for, are we fine tuning for professors of mathematics? Are we fine tuning for mice or computers? I showed a slide about that. Ultimately, I feel that consciousness really is fundamental. And I feel that what we really are tuning for is consciousness. And I will talk about this more in the second lecture. This isn't necessarily the mainstream view, even among the people who are interested in the multiverse. But I think we are fine-tuning for the consciousness. And that means something about the nature of time. And that in itself is going to relate to this final theory of physics, because I think the final theory of physics, which is going to amalgamate relativity theory and quantum theory, is also going to tell us about consciousness, and it's going to tell us about the mystery of the passage of time. Now, the mystery of the passage of time is also related to this whole issue of the second law of thermodynamics, and therefore the initial state of the universe. So this question has been, my answer has been rather long-winded, but the point I'm making is that I think that it is very relevant, that the nature of the special beginning of the universe is very relevant to the whole issue of the nature of consciousness. So when you ask the question, when you talk about the multiverse, are you allowed to have multiverses in which you don't start off with a low entropy state, or are all your multiverses going to be like ours, where you've got a low entropy state? I would say that in some sense, the ones which are going to give rise to us with a flow of time have to be this low entropy state. Now, that's a long answer, and it's probably not very convincing, but that's at least I think the best I can do at the moment.
Thank you very much, Bernard. I think we should also give space to other people who.
Of course.
Yes, thank you, Shantina, for coming in. Really interesting question. So yes, we've got about 10 minutes left for Q&A. So I'm sorry if we won't be able to go through all the questions, but I'm sure that the next session we can cover more ground by opening up. So to ask a question, you can use the raise your hand function at the bottom of your screen under reactions, or physically raise your hand, or ask it in the chat and I can read it out for you. Anyone?
I mean, there are some questions in the chat box, I notice.
Yes, well, I'll read this one because I actually had this question as well. So it comes from Pam, who asks, are the various cosmological multiverse models discussed mutually exclusive, i.e. one can only be true or none are?
Well, that's a very interesting question, because Some of them aren't. I mean, for example, I talked about the inflationary multiverse, which is a multiverse in space, and I talked about the cyclic multiverse, which is a multiverse in time. Now, by and large, there's no reason in principle why you couldn't have both of those, but very often the people who want the cyclic models are not the people who want the inflationary models. For example, I mentioned the cyclic model, the ekpyrotic model, which Turek and Seinhardt favor. Now, that's a cyclic model, but that model specifically goes against the inflationary, the eternal inflation model. So those two models themselves are not compatible. So you either are going to go for the ekpyrotic cyclic model, or you're going to go for the inflationary model. However, you could, that's eternal inflation. You could envisage cyclic models which go through an inflationary phase. You know, each phase may have inflation. So in principle, an inflationary model doesn't have to be inconsistent with a cyclic model. I mean, you know, you could have a series of expanding and recollapsing models, each of which go through an inflationary phase in their early stage. So those two are not incompatible. However, when you, as I said in my answer to Shantina, when you start asking about the compatibility of the well, let us take, I talked about the string landscape model, okay? The string landscape model was the prediction that you have many different vacuum states, 10 to the 500 vacuum states. And then it said, well, we have to be in the subset where the cosmological constant isn't too large, because otherwise we don't get galaxies. Again, that could be compatible with an inflationary scenario, because you can have both inflation and string landscape. So those two sorts of models are compatible. Where it gets difficult is when you start talking, when you start talking about the many worlds, the ever many worlds picture, because that in some sense seems to be a different type of multiverse, because that's a multiverse. The many worlds is happening now. You know, the idea is that the universe is constantly splitting now, whereas all the other multiverses are, you know, they're separated in space and separated in time. The Everett multiverse is happening now, and it's true we can't interact with the other universes. So my own personal view is that the Everett multiverse is a different sort of multiverse, and it rather confuses things from my perspective. And then the quantum cosmology, you know, the multiverse in the other dimensions. You remember I talked about the multiverse is spread out in the fifth dimension. Again, that could be that can be associated either with the ekpyrotic model, where, you know, I had colliding brains producing the cycles, but it could also be in an inflationary model. You can have inflationary models which have an extra dimension. So I can have for example, I can have a single brain, for example. Brain cosmology has a single brain in this five-dimensional space, and you can have inflation you can have brain inflation. So in that case, it's compatible. So the answer to the question is it depends very much. I mean, bear in mind that all these models are speculative anyway, and some of them are compatible with each other and others aren't. But I think what you can say is that there's certainly much more than one model of the multiverse, and in some sense you could have, I mean, when Tegmark talks about his 4 levels of the multiverse, in principle you could have multiverses at all the different levels. There could be a hierarchy of multiverses, but generally speaking, people tend to be keen on one rather than the other, because you know, I like to say, well, if you're a skeptic of the multiverse, in some sense, the more multiverses there are, you should at least be open-minded that one of them might turn out to be correct. But sometimes people react the opposite. They say, well, there's so many of these multiverses, I don't like any of them. You know, if you've got more than one multiverse, that's too many.
Okay, great. Well, thank you. Sorry, Bruno, I'm just looking at the time. Are you happy to take 3 more questions?
No, I'm in no rush at all. Because
okay, perfect.
It's 7 o'clock here. It's 6 o'clock.
Okay, fantastic. Well, then we'll go to Mel first, who couldn't get the raised hand
Okay.
Thank you.
Yes.
So I'm of the shut up and calculate school of
Sure.
quantum mechanics, which I'm sure you're familiar with. These kinds of discussions you do over the departmental lunch table and Saturday night with a little bit of wine and a little bit of weed, but at the end of it, you say, look, we have machinery that works, we don't understand it, but with the first 3 chapters of any graduate quantum mechanics book, it doesn't even have to be Dirac, and today's supercomputers, you can generate most of chemistry. You can predict stuff that Wigner in the 1930s said you couldn't, because chemistry is the part of physics that's too hard for the physicists. Well, it isn't anymore. So when you talk about these different points of view of yourself and Ellis, you say, he says it makes no testable predictions. And I think you said, maybe not directly, but indirectly, well, actually it does. There are some testable predictions that it makes. So I'd like to hear about 1 or 2 of these.
Sure. Okay. I mean, I had a slide on that, but I'll just say, well, first of all, Mel, you're right. Most physicists are of the shut up and calculate kind, and that's fine. But I'll point out it is Saturday evening, and therefore it's the right time to answer.
It's Saturday morning where I am.
Oh, sorry, Saturday morning where you are. Yeah. And it's also true that, the people who work on, the interpretation of quantum theory are I think only a relatively small subset of physicists, because most physicists probably just work on quantum theory and they apply the equations, but they know it works. However, there's no doubt that trying to understand the fundamentals, the basic interpretation of quantum theory, the collapse of the wave function and non-locality and all the other things, to me is really fundamental, even if it doesn't affect the people who are doing more, the practical technology associated with quantum theory. And I mean, for example, I know Basil Hiley was one of the participants, and the work that he did with David Bohm was on the interpretation is so fundamental. And what I do think is that when we have our final theory of physics, the marriage of relativity and quantum theory, it has to say something about these fundamental issues like the interpretation of quantum theory. I mean, it seems to me in the whole history of science, there's always, at the extremes of science, there is always a border between, mainstream empirical science and philosophy. And there are certain issues which you might regard as being in the philosophical domain rather than the practical scientific domain. And indeed, you might say that M theory is like that, because at the moment we can't test M theory. We can't get, accelerators don't get to the right energy. At the moment, we can't test the multiverse because we can't see the other universes. But the point is, though, that as time goes on, issues which are in the philosophical domain somehow become part of the genuine scientific domain. So, for example, I think that issues about the interpretation of quantum mechanics might now be regarded as more in the philosophical domain or the philosophy of quantum theory domain, but I think they have to eventually become, subject to proper, and indeed they're subject to experiments. I mean, people are doing experiments on, going back to aspects in people. Features of quantum theory which were originally regarded as more philosophical, like non-locality, are now hard physics because people do experiments. And now you've got the development of quantum computing and things like that, where these sorts of issues of, how you interpret the parallel worlds and things become actually practical, functional questions. So I would say that although it's perfectly understandable that most physicists are only going to talk about these things at lunchtime and on Saturday evenings, I mean, I predict that eventually physicists will be talking about these, during the working day as well, because I mean, I think they will, in the final theory of physics, that will be really crucial. Now, obviously, most physicists don't work on the final theory of physics. Now, then you did ask me, well, are there any observational signatures of M theory and the multiverse? Now, on the face of it, it's hard to test M theory because the energy involved right up to the Planck energy, 10 to the 19 GeV, which is way beyond, you know, what we can test with the Large Hadron Collider, where we're up to, what is it, 100 TeV or something like that. There is a possibility, though, that, you know, for example, these extra dimensions are normally assumed to be on the Planck scale, but they could in principle be extended. That's what happens in brain cosmology. You have one dimension which is extended. So if you've got large extra dimensions, there was a hope that you would be able to detect these at the Large Hadron Collider, and people look for that. Now, at the moment, they haven't found them, and that doesn't mean they're not there, but they're at a higher energy. But what I mean is there is a chance that you will eventually be able to detect some prediction of M theory. I mean, large extra dimensions are only one version of, you know, of M theory, but I do think you could, in principle, be able to test that, even though we haven't got the evidence at the moment. As regards the multiverse itself, well, there are various ways that you can do this. For example, one prediction is that these in the version of the multiverse which I described, you know, the bubble picture, the bubbles could have collided at some stage, and then the bubbles would produce scars on the sky, the microwave radiation. And people have argued that you could get evidence for collisions with other universes in this particular variant by looking for scars in the microwave sky. Now, people haven't yet done that, but they're still able. People are looking for this, and they're doing simulations to see what they would look like. The same is true, for example, of Roger Penrose's conformal concyclic model, where he already claims that there are some signatures in the microwave background which correspond to things that happened in the earlier universe. So that, if you like, will be observation of another part of the multiverse. But there are other things. For example, I don't want to get too speculative, but for example, one always says you can't see beyond the horizon. But you know, within relativity, you have things like wormholes, you know, and wormholes can, in principle, connect great distances, you know, way beyond because they're not subject to the speed of light constraint. So in principle, I don't see why you might not go into a wormhole and come out in another universe, or even come back again. Now, of course, wormholes are equally, you know, speculative as the multiverse. But I mean, I can foresee ways in which you might eventually get evidence for other universes, even though we don't have the energy now, the evidence now. Now, maybe we never will. I mean, but what I like to say is, I say multiverses are what I call meta-cosmology, which is in this sort of border line between philosophy and cosmology. It comes out of physics, but we don't yet have the empirical evidence. Maybe we never will have the empirical evidence, and then you have a serious semantic question of whether you're going to call it ever will be science or not. But on the other hand, I like to think there is a time, you know, that there is a hope that it will be subject to empirical observation. So I've just given you a few examples of how it might in principle be detectable, but we don't yet have the definite evidence. Although Roger Penrose claims he does. Roger Penrose claims that he does have evidence for the previous collapse phase.
Great, thank you.
Thank you, Mel, for that question.
Thank you, Mel, for coming in, and thank you, Bernard, for your very big answer.
Yeah, I'm sorry, my questions or answers are long.
No, that's fine. That is fantastic. Next question. We'll see what time it gets, but we'll take the next question from Igor, who had his hand up earlier.
Yeah.
Hi, Professor Carr. Two brief questions. How do you include the idea of the black hole and singularity into the fabric of other alternative universes? And the second question is, in your models, how do you define consciousness?
Oh, right. Well, the first question about black holes. I mean, of course, there's a deep connection between cosmology and black holes. You have the singularity in the center of the black hole. You have the singularity in the center, at the beginning of the universe. And indeed, there was one particular version of the multiverse which I didn't discuss, which I'll mention now. This goes back to Lee Smolin. Now, Lee Smolin actually is a skeptic. He's not really keen on the multiverse. But he has this idea that when a black hole collapses, the collapsing black hole generates a baby universe. And it gives birth to an expanding universe. And indeed, our universe, our own universe, may have actually resulted from the collapse of a black hole. Because bear in mind, no one knows what happens at a singularity. So all you're doing is you're replacing the singularity by like a little wormhole, which generates another universe. And then, so he has this idea that the universe, when you form a black hole, you will necessarily generate universes which are going to maximize, where the constants vary, but the constants vary so as to maximize the number of black holes. Okay, it's a sort of, it's like an evolutionary picture. It combines, some idea of mutation, because the idea is you mutate the constants every time you create a new universe. And then you naturally, through this sort of selection effect, you end up with the universe which is most amenable to black holes. Okay, in other words, you're going to get more black holes in the universe than you would in most other universes. Now, in fact, we know the universe is full of black holes. I mean, there's billions of stellar black holes. I work on primordial black holes. I like to think the universe may be full of primordial black holes, explaining the dark matter, but they're supermassive black holes in the centers of galaxies. Black holes are everywhere. So there is this one particular version approach which says that the universe is fine-tuned not for life but for black holes. So it's, if you like, a competing theory, but I still regard it as a multiverse picture. But the difference, there's an important conceptual difference. Normally when you talk about the multiverse and fine-tuning, you're assuming that you're lots of different universes and a very small fraction are going to be suitable for life. Okay. And that's why it's a natural selection effect. That we have to be, the idea is that you've got different constants in all of them, but we're necessarily in one of the universes which have constants in the right range of values for life to arise. But in Smolin's picture, it's the opposite, because in Smolin's picture, the universe is evolving so that most of the universes are supporting life. So it's quite a different picture, because because it's like in evolution, you evolve the form of life which survives is the one which is most compatible, and therefore the universes which produce lots of black holes, they're the most populated ones, because they're the ones that give birth. The universes which have progeny are precisely the ones which are tuned to make progeny. So that picture is rather different from the multiverse picture which I've described, but it's a very interesting one, and it's just as speculative, of course, because nobody has any reason for believing that when a black hole collapses, it really does generate another universe. But I mean, that's a natural answer to your question, because it does link black holes and cosmology. I mean, in some sense, the cosmological Big Bang is like the time reverse of a black hole collapse, because I mean, you're collapsing in a black hole, everything collapses to a singularity. In the Big Bang, everything comes out of, except it's a white hole rather than a black hole. And in fact, there's even there is a version of in brain cosmology, which I talked about. In brain cosmology, you can think of the universe as emerging from a 5-dimensional black hole. So this is more speculative, no more speculative than Smolin stuff, but nevertheless, so there is a fascinating link between black holes and higher dimensions and cosmology. Now, your second question was about consciousness. Well, I'm in my final lecture. I'm giving a lecture called "Is the Multiverse in the Mind, or is the Mind in the Multiverse?" And I'm going to focus on consciousness and mind in that lecture. So I'll postpone answering that till well, nearly 4 weeks, I guess it is, because I think, to me, I'm fascinated in the question of consciousness. I mean, everything I've said so far about cosmology, I'm talking in my professional capacity as a cosmologist, and therefore, you know, it may be speculative, it may be wrong, but at least these are the sort of ideas cosmologists talk about. In my next lecture, I want to argue why I think consciousness is fundamental, and I want to argue how literally you can get mind in this final theory of physics, which marries relativity and quantum theory. I'm going to argue that that theory is going to contain consciousness. I mean, this is what people like Penrose say, you know, that the final consciousness is missing in physics. Most physicists say, well, consciousness is not part of physics. I mean, it may exist, it may be fundamental, but it's not part of physics, because essentially physicists deal with the third person perspective. You know, they're not interested in the first person perspective. So consciousness is forever out of physics. However, I actually don't accept that view, because I think that, I mean, obviously there are hints from quantum theory that, you know, consciousness, or at least observing, might be relevant. And I would say that the fine tuning is also another, it's coming from arguments in physics, is another indication that consciousness is fundamental. So I want to have a theory which explicitly somehow puts mind into physics. And I have a very specific way of doing that, which is even more controversial than anything I've said about the multiverse. So I'm leaving that till the end of the session. Yeah.
Looking forward to that. Yes, thank you. Thank you so much, Hugo, for coming in. So I'm just looking at the time, and unfortunately we should really close down. I'm really sorry, Mike. And
I can see the chat. Is there any way you can preserve the chat? Because I can always
of course, the chat will be reserved, also be sent out with the recording. So this will be saved.
So people who haven't managed to ask questions, I'm taking, there's a lot of chat here, so I can't remember it all, but you'll have this preserved anyway.
And presumably you will allow, you're happy to take email as well, if
yes, indeed. Mike, if you've got my email address, just send me an email.
I think I have, yeah. If not, I can certainly get it from Basil or from Martin or one of you. Yeah, don't worry. No.
I always prefer to answer it.
No, it's okay. I completely understand why James needs to bring things to an end. And in fact, I think from what you know, the little note you put out there about where your second talk is going to be going, yes. The question I very much had in mind might in fact be more pertinent to that anyway. Okay. So, but we'll correspond anyway.
And also there's a general discussion session at the end on the 24th.
There is indeed, yeah. And can I just say though, before James comes into, thank you, you know, thank you for an absolutely fascinating, you know, magnificently clear, you know, and magnificently in terms of the sheer amount of ground you managed to cover. Just wonderful talk.
Oh, well, thank you. I'm afraid that's why I went on for 90 minutes, but thank you.
No, it could have gone on for another 90 quite easily. And
okay, thank you.
I'd just like to repeat what Mike said. This has been really fantastic session, Bernard, and we are really, really grateful that you participated in this. So thank you so much. And also thank you for everyone who joined, was asked their questions, tried to ask questions, or contributed in the chat. Thank you all for joining us. Just before we go, I'd just like I have a few housekeeping things to announce to you all. The first one is that we will be shortly opening a Sutra Circle for you all. Sutra is our online forum where all the participants here and the speakers are invited to join. So it's a great way for you to continue these discussions online with your peers. Let us know if you don't receive that link. You should receive it tonight or tomorrow. If you don't receive it, just let us know and we'll send you the link again. And then finally, hope to see you all tomorrow for the session with Paul Tappenden, who will be discussing dendritic quantum mechanics. Finally, you can contact us on our website in the contact us section, or you can write us on social media, Facebook, Twitter, Instagram, or even email us directly at james@powercenter.com to contact me, or Eleanor@powercenter.com to contact Eleanor. Thank you all again for joining us. Thank you so much, Bernard, and we'll see you again soon here at the Power Center.
Okay, bye-bye.